Welcome to this public meeting for our statewide beach bacteria Tmdl. My name is Jim Hallmark, and I'm an environmental engineer with the Iowa Department of Natural Resources. And I'm going to give a short introduction here to the topic, and I will be followed by Jeff Burkus, who will provide some general information on the project. He will be followed by Jason Palmer, a biologist with the department, who will discuss some of the monitoring efforts related to this Tmdl. And following Jason, I will end the presentation by discussing the development of the Tmdl for the 3 beaches contained in this project. One thing to note is that we are currently in the public notice period for this addendum to the statewide beach bacteria Tmdl project, which will run through October 4th of this year. If you have an official public comment that you would like to make, please send that to either myself, Jason Palmer, or Roger Bruner at the respective emails listed on this slide. And with that, I'll turn the time over to Jeff.
So I'm going to lead off this presentation and just kind of get into a few things. You will note that this is the addendum to this. This is kind of part 2 of our approach to dealing with the bacteria issue at our state beaches. Part 1, there's a presentation online that came out last year in 2020, basically at the start of the pandemic. It was one of the first things we did after the pandemic started, was to get a video recorded for this particular project. There is a little bit more detail in some of the background of that first iteration. If you're interested, we will put the link to that video below, so you should be able to find that easily enough. But we're going to be focusing here on the new beaches that we're adding to this document. And my job here today is to go through a couple of slides to kind of set the tone here. So that first original document, the first 3 study lakes that we used to build the statewide beach bacteria Tmdl, that came out last year, were Clear Lake, Hickory Grove Lake, and Night Eagles Lake. You see those circled here on the map of Iowa in green. So those have been approved by the Environmental Protection Agency, that they are ready to go. These lakes that are circled in orange, those are the lakes that we're going to be talking about today that are in the addendum. Brushy Creek Lake, Lake McBride, and Lake Aquabi. Our plan is to continue to gather information to fit it through the filter that we have established, that we will talk more about, to see if more lakes fit into this approach and can be eligible for some of the implementation work that we are starting here with our partners with the 319 program. But today we're going to be working on these 3. The hope is that every year we will add more as we get more information and as we confirm that more of these beach systems fit into this fingerprint that we're going to be talking about more about today. What that is basically we figured out a while ago, a couple years ago, that there was a pretty big disconnect between the compliance point where we take our information for water quality data that really represents what's happening in the watershed overall, the big picture watershed, and what was maybe happening at the beach where we take beach specific information, particularly where we have bacteria issues. And as you can see just from this map of Big Creek Lake, which is just a really good map to show this, the distance, the physical distance between where we would take the compliance sample all the way down here at the bottom with that arrow down here, and where you'd be taking the beach samples in that big circle there. There's just a huge distance and things are happening in a different way. And so it's not necessarily surprising that we, sometimes have a disconnect between those 2 areas just because of the physical distance. But it was very clear that we had different things going on at the beach than we did down here at the compliance point. This is again, this is Big Creek, just for illustrative purposes, and zeroing in on some of the sampling that Jason did early on in this project, but just to show you just how much sampling was done on the beach sand and in the near shore volume of the water that interacts with that beach sand. These are the sampling efforts that we were collecting to try to make this case that there is a big difference between those 2 areas. Anytime that you see a map, though, I wanted to draw your attention to that. We will have points that will help orient you to where we're at. There's always going to be a compass rose here. We're always going to point you in the north direction so that you can get an idea of which direction you're facing or which direction you're looking at. There's always going to be an inset map so that you know what part of the state we're talking about. This is Big Creek's lake here, so we're in the center of the state here. And there's always going to be a scale so that you can see just how long or how far the distance is between 2 points. So anytime that we use any map on this presentation, or anytime we use a map inside of the document, you're going to find those things to try to help guide you. One thing, and I've already used the term watershed, I think it's always important to go over the definition of watershed. The blue outline here, this happens to be Hickory Grove Lakes watershed, but anytime you see us have an outline of a land area and have difference between the background, what we're indicating there is what the watershed area of the landmass that drains to this specific water body. So if a raindrop falls anywhere inside of this area that's outlined in the darker blue, it's going to eventually find its way into that water body. Any drop of water that lands outside of it is going to go somewhere else. And so as water quality relates to what's happening on the land, a lot of times we're most interested in what's happening inside of the watershed with relation to water quality with that water body. So watershed is this whole area for this whole lake. Beachshed is the land area that drains directly over the beach. So just think of it as a very small part of the watershed is the beachshed. So just that area that's draining directly to and over that sand on the beach that interacts here with this nearshore volume of water on the beach. A couple other points that I wanted to make sure that we are all on the same page. Assimilate is a word that we will use from time to time. And basically what assimilate means is just how much of a pollutant the water body can process. There's going to be a calculation that we can do that basically says this volume of water given this type of water body, that can handle this much pollution of each kind of pollution that we're talking about. So if you hear the word assimilate, that's what that means. Impairment, that is an official sounding word. Basically, it means that the water quality is not meeting our expectations, those expectations of our water quality standards. Anytime that we have enough monitoring to be able to evaluate the water quality, we evaluate those against the water quality standards. And when they are not meeting certain parameters, they become impaired. And then we come in and we try to figure out what's going on with those water bodies. Point and non-point source pollution. Point source pollution is basically any type of pollution that's relevant to the document that we're working on that is permitted. Sometimes people will say, I can point to it, like I can point to a pipe. That's right in most circumstances, but for us, we really like to refer to it more as permitted sources of pollution or point sources. Non-point pollution would be basically everything else, pollution that comes from a diffuse manner, things that are running off overground or what have you. Basically, they're not permitted sources. In the statewide beach bacteria, Tmdl, and these small lake watersheds, for the most part, when we work in, we don't deal with a lot of point sources. We're dealing with mostly or all non-point sources, and that's the case here as well. Tmdl, we've talked, I've used that term a few times, especially it's in my job description. And so what does Tmdl mean? It stands for total maximum daily load. That's the official name of the part of the Clean Water Act and the official name of our program. What that means is that it's a specific number that we're calculating, that we're showing what the capacity of that water body is to process that amount of pollution. And I've always liked to use this picture, which is a pack mule that's up in the air. He has way too many boxes. That's way too heavy, and he has flown himself up into the air because that load is just too much for him to be able to carry. But if you can imagine at first, with no boxes on that cart, that pack mule was able to run around and do anything that he wanted to. You start putting up more boxes onto the cart, and it got a little harder for him. It gets a little harder, And at some point, he's not going to be able to do the work that you would expect him to be able to do. And that's what we're talking about here with water quality, is that if you imagine the water body being the mule and the boxes being boxes of pollution, there are a few boxes of pollution that you can put onto the back of that water body, and it still can meet the expectations that you expect of it. But if you put too many boxes onto that cart, you're going to start having problems. It's not going to work very well, or we get to the point here where we're up in the air, we can't go anywhere. And so the idea of a TMDL document is to calculate the number of boxes that we need to remove from the back of that cart to be able to get that donkey to get back down on the ground and be able to carry it around, to get the water body back down on the ground, and be able to meet the expectations that we expect of our water bodies. What we'll also find in our documents is an implementation plan. This is something that we find that's very important to make sure we're spending time on. This is not prescriptive. This is not saying, please do ABC on this part of the watershed or what have you. They're more a guide of what we believe will work for that particular pollutant in this particular part of the state. And that information can be used by planners to help locally led plans get developed. Those two things together, we call that a water quality improvement plan. And that is the official name of the document that we produce throughout the TMDL section. So you'll see water quality improvement plans. Other presentations for other water quality improvement plans that we've been developing are on on this YouTube channel as well. That's what that means. That's what that term means. So those two terms, TMDL and water quality improvement plan, can sometimes be used interchangeably. We try to make sure we're saying water quality improvement plan when we refer to the document, but know that sometimes TMDL is a very easy shorthand for us, and we will do that as well. This is a very complicated chart that Jim is going to have more time to discuss and talk about. And Jason's also going to have some interesting charts and graphs. And what I'll say is the great thing about recording these public presentations has been that it gives a really unique opportunity for the viewer to be able to pause, soak in what it is that the graph is trying to say, rewind for the presenter to be able to give you the explanation once again. Something that you wouldn't necessarily have in a live setting is that opportunity to slow down and make sure that you understand what it is that we're trying to say, or have the speaker repeat it just by using the repeat button or pulling back on the slider a few seconds to hear it again. So anytime that I would see a graph that I'm getting presented to me in a presentation like this, I'm always going to do a couple of things. I'm going to check what's happening here on the axis. I'm going to read what they're trying to tell me this is measuring on the y-axis. This is called the vertical axis. And on the x-axis, I'm going to do the same thing. So here we have the month of the year, and we have the E. coli concentration. Okay, so, and then I'm going to find a key, and I'm going to find what all these little symbols mean. And so again, this is a particularly busy slide, the graph. There's going to be a lot of information. It also happens to contain a wealth of very important and interesting information that helps us understand what's going on in this particular water body. So it is incredibly important for us to understand what's happening here and express this in one page of a document or in one slide. So while it does have a lot of information, and it may be something that takes some time to truly understand, we think that that's worth it because it does express some important things. So keep that in mind as you go through this. And so I'm going to hand you off into the capable hands of Jason Palmer, our biologist on this project. And then on deck, and who's going to close it out, is James Hallmark. So thanks again for joining us for this public presentation.
Thanks, Jeff. Yeah, so today I'm going to talk a little bit about the lead up to this second set of beaches that we're including in the statewide beach only back TMDL. So back at the beginning of this, when we first set up our original project, we were asking questions about where the impairments originate from, How does the impairment at the beach relate to the broader lake condition? Where might be the sources of bacteria at the beach? And then also trying to investigate how we might best manage the issues in the systems that we're monitoring. And so, as Jeff mentioned, we have a longer documentation of this on our initial investigations that took place on the first 3 systems, and we've kind of repeated that monitoring process on the next 3 systems. And so, looking at our original questions for our monitoring design, we wanted to determine whether there was a gradient in condition in bacteria concentrations, either in the terrestrial zone in the sand or in the lake, sort of in that beach swimming zone on out into the open lake. Were there associations that we can identify between what was happening in the terrestrial environment in these systems and what was happening in the beach swimming water? And also, were there associations or differences between what was happening in that nearshore swimming area and what we observed throughout the rest of the open lake, and that might be more reflective of that broader watershed that Jeff was describing a little bit earlier. And to do that, we collected samples from different areas of the lake environment. One of which was the sand. We set up transects on the sand, radiating, from close to the beach waterline on out and further up the shoreline. And we collected sand cores and analyzed what the bacteria concentrations were inside those sand cores. We then also looked at the broader, open lake environment, taking samples from areas where we might have, water coming in from various inlets, samples at the compliance point or oftentimes the deepest part of the lake, and also have established a transect that mimics the spacing and collection methodology that we use at the beach on a different shoreline of the lake that is more representative of the broader lake condition versus what we see at the beach. And then we also honed in on very specifically what was happening in that nearshore beach environment and that beach zone. So the first of the 3 lakes that we looked at for this beach-only plan was Brushy Creek Lake, which is located kind of right south of Highway 20 in north central Iowa. Over the 2-year period that we collected data in this system, we saw that the inlet points and compliance points in the lake averaged about 144 mpn per 100 milliliters of E. coli. And then when we look at our alternate transect, or the zone that kind of mimicked the same spacing that we were looking at in that beach environment, we only had an average concentration of 22 mpn per 100 mils. And then when you look at what was occurring in the shoreline area close to the beach, you can see as you move from the open lake environment in close to the near shore zone, you go from averaging around 19 to averaging 232. So we can see that we don't tend to identify gradients that would show high concentrations moving through the system and to the beach. What we see is a reverse of that, where we have our highest concentrations sort of in close proximity to that near shore sand environment. And this is a similar trend to what we saw in all of our other systems that we looked at in the first phase of this plan. And it's the trend that I'll show here moving forward with the other 2 systems that we looked at. So for Lake Aquabi, kind of south of Indianola, we saw those same associations that we saw in the previous plans and that we saw in the Brushy Creek Lake system, where we had open lake averages, in this case, only 37 mpn per 100 mils. Our alternate transect was very low as well. So the water collected along this transect was very low in bacteria concentration. Moving towards the beach, that open lake environment, immediately adjacent to the swimming zone, had very low bacteria concentrations. And then again, when you get closer to the shoreline and you're in close proximity to that sand and recreational zone, you see a general increase in bacteria. Again, our other system, Lake McBride, north of Iowa City, adjacent to the Coralville Reservoir, we saw very, very similar associations where, water moving through the system, going or coming off of little inlets, and then our compliance points all had very low bacteria concentrations. Our alternate transect, same thing as the other systems. The open lake environment immediately adjacent to the swimming zone, very low bacteria concentrations, barely above our detection limit of 10 MPN. And then again, once you get very close to the shore, in association with that sand environment in that swimming zone, we see an immediate increase in the concentrations of bacteria that we observe throughout our numerous trips to sample in these systems. And so this is a trend that we're seeing develop in many of the systems that we analyze for this fingerprint, as Jeff put it, where when we identify that there's a problem, with E. coli in these swimming zones, and then we start to look at what's happening in the rest of the system, we see a very pronounced disconnect between the rest of the watershed, the rest of the lake, and that swimming zone environment. Zooming in on that, just thinking about that beach zone and that recreational environment, looking at the data from our transects that we established at the beach, we have our ankle, knee, waist, and chest deep samples in that swimming zone, and then we collected data from the swimming rope on out in about 30-meter intervals out into that open lake. And as you can see by the relative scale, the relative sizes of these dots, you can see a pretty rapid tapering off of bacteria concentrations as you move away from that shoreline environment. In every system that we've collected data, this zone right here along the lakeshore is always the highest in concentration. And one of the things we look for when trying to determine whether or not a system is demonstrating conditions that would be consistent with that beach-only plan or that beach-specific driven impairment is to see whether or not there are differences between this swimming zone environment and then the adjacent open lake environment. And in all three of these systems, and with the other systems we've sampled in the past, there is definitely a statistically significant decline in the bacteria concentrations as you move into the open lake away from that near shore beach environment. And so when thinking about that, it drives us towards another part of our sampling, which was the terrestrial zone sampling that I showed earlier with the sand cores. Something's happening that's specific to that beach zone environment that's causing these issues to manifest. Because if you remember back to the slides that I showed of the open lake areas where we had the alternate transects, we were sampling at ankle deep, knee deep, waist, chest deep, along a shoreline that didn't contain sand and a swimming beach environment. And we did not see this trend. We did not see these elevated levels of bacteria on any of them. So when we look at the information that we collected, we saw that there was a corresponding sort of zone of influence, if you will, where these areas in tightly adjacent to the water line, both in the water and in the sand, contained the highest bacteria concentrations relative, to their areas. So in the terrestrial zone, we saw a decrease in bacteria as you moved upshore, and in the water, we saw a decrease as you moved out. And this zone, in tight proximity to the swimming area, has very high bacteria concentrations. So that terrestrial zone contains large quantities of bacteria. And what we saw over the course of the monitoring season in these 3 lake systems, as well as in our original data collections when we kicked this project off, was that as those bacteria concentrations increased in the terrestrial zone, we also saw corresponding increases in that swimming, recreational swimming zone environment. So there's obviously a correlation of condition between these 2 zones. And to think about that, or to put that into context of just how impactful the conditions in the beach can be to the swimming zone environment, you have to think about what the concentrations are of bacteria that we observe in the 2 environments. So when we collect our sand from the beach, we're collecting, a tube of sand from the surface, and we've got X number of centimeters of cubic centimeters of sand, and 1 cubic centimeter of sand equals roughly 1 milliliter of water. And so our water was reported in 100 milliliters, and our sand was reported in, amount of bacteria per gram. And when you correct to put them on an equivalent scale, what you see is that sand area of the recreational swimming environment had an average concentration on the 3 beaches from 900 to 24,500 times higher in bacteria concentrations than what we observed in the water. And on an individual sampling trip to Lake McBride, we observed that the sand had bacteria concentrations in excess of 180,000 times higher than what we observed in the water. So looking at this box on the side doesn't really even do it justice to the disparity or the discrepancy between the amount of bacteria that can be concentrated in that nearshore sand and the amount of bacteria that we observe in the water. And so what you have is a high concentration of a pollutant of concern in close proximity to our measuring point or our response point in the environment where people are recreating. And so looking at that and thinking about the gradient from the shoreline area or the sand environment, and then the water, and thinking about the transect moving from close to shore on out into the open lake, this graph shows that corresponding, bulk, large quantity of E. coli, and then the movement of that material into the lake environment, and then the dilution of that material as you move further and further and further out into the open lake environment. Recreating these graphs on any of the systems that we collect these data on yield similar results, with always having higher concentrations in the sand, lower concentrations in the water, and then a fairly rapid drop-off as you move outside of that recreational swimming environment. And so thinking about what the mechanisms that are at play in a situation like this, you can envision that gradient from the shoreline where you have a slope coming down the beach, hitting the water, and then you've got your water volume moving out. And so this accumulation of material is sitting in a very easily mobilized position. And so thinking about how this material can make its way from that very important zone of beach sand into that recreational environment, one only has to think about several very kind of simple gravity-based processes. So here's a picture of a downpouring rain causing water to move through this zone, which can have tens of thousands of times higher bacteria concentration, and delivering that material into that open swimming zone environment. So this is a very obvious mechanism at play in these systems. Something that folks don't often think about are that there are other mechanisms in which you can get this material into your swimming zone environment. Because this area in tight proximity to the shoreline contains pretty large amounts of bacteria, even the wind and waves, coming on shore can sort of re-entrain that material and bring it into that swimming zone environment. You'll also notice that a lot of times on our beach systems, we can have waterfowl or shorebird usage, which can add to the bacteria issues that are at play in the system. And this material can also be mobilized via either the runoff or wave action and end up in that nearshore recreational zone. Another issue at play that creates a situation where it's tough to predict when you would have high concentrations of bacteria. One could go to the beach and see lots of onshore waves, or come right after a runoff event and think, oh, maybe I should avoid this water. But another issue is that you could get direct defecation of material even on a day where you have very calm water, and you could get bacteria concentrations to increase locally because of that material being directly deposited in the water itself. So the one thing that all three of these have in common is that they all take place in that recreational zone environment, and our assessment of the conditions that need to be improved are going to need to focus on that nearshore environment and activities that take place in that beach capture shed that Jeff described earlier, that would help minimize the movement of this material into the lake environment. And so the next steps that we've taken in this is to develop TMDLs to look at how to adjust or to address these issues, and what sorts of load reductions might be necessary to make it so that this beach has, less in the way of bacteria problems. And that's where my colleague Jim is going to pick up and talk about the next step in the process of utilizing these data in these systems. Thank you.
Well, thanks, Jason. As mentioned, my name is Jim Hallmark, and I'm an environmental engineer with the Department of Natural Resources. And I'm going to discuss the development of a water quality improvement plan addressing the E. coli impairment for these three beaches. As part of the water quality improvement plan, and what I plan to discuss here today, will include the following points. We're going to determine the potential pollutant sources. Going to talk about our total maximum daily load calculations, how we came up with our TMDLs for E. coli at each of these beaches. And then I'm going to follow up with some implementation plan and list some potential solutions to resolve this E. coli issue at our beach areas. As we talked about before, there were three lakes included in this water quality improvement plan. There's Brushy Creek Lake, Lake Aquabi, and Lake McBride. And Jason did a great job in laying the foundation of how we developed, or how we came to develop our water quality improvement plans for these lakes. And so here in each of these beaches, we've talked about our beach shed area, which we've highlighted in yellow. And the beach shed areas for these three beaches range in size from 3 acres to roughly 11.5 acres. We've also identified the swimming area, or the nearshore beach volumes, which we've highlighted in red. And the volume of these swimming areas range from 1 acre feet to 1.5 acre feet, with 1 acre feet being the depth of water over 1 acre of land. So for 1 acre foot, there would be 1 foot of water over 1 acre. And 1 acre is about the size of a football field. The swimming area was defined from edge of sand to edge of sand along the shoreline, and extending out a distance extending out from the shoreline to a depth of 4 feet, which is roughly our chest depth, and then extending out an additional 3 feet from there. So with this information and the information that Jason has provided, we're able to start working on a water quality improvement plan and focusing in on the beachhead area and the swimming area or the nearshore beach volume. And since the process used to develop a TMDL for all the beaches is the same, I'm going to walk you through one using Brushy Creek Lake. Water quality improvement samples were collected in each swimming area at each beach as part of the state's ambient beach monitoring program. And these were the samples. These samples were used to identify impaired lakes. And Jason talked a little bit about that in his presentation. And the samples collected as part of the state's ambient beach monitoring program were independent of the samples that Jason collected over his 2-year study of each of these lakes. So once we have our data and we begin to analyze, we want to analyze it, we're going to plot it. But first of all, in our plots, we have here a graph. And on the y-axis, we're going to plot our pollutant of concern. In this case, it's E. coli. And we're going to plot it as a concentration, the number of organisms per 100 milliliters. And that's along the y-axis. Now, along the x-axis, we have plotted it by time. In this case, we've identified it as months. And by plotting it in months, we can break it up into seasons, such as our spring seasons, our summer seasons, and our fall season. Our spring season, and our spring season is data points that were collected or samples collected from March 15th to May 23rd. Our summer season are data points collected or data collected from May 24th to September 7th. And our fall season is from September 8th to November 15th. We've extended the summer months 1 week on each end, so we can include the Memorial and Labor Day holidays in our summer sampling periods. By breaking it up into seasons like this, into spring, summer, and fall, it's also easier to identify the times of season in which E. coli might be most prevalent and most of an issue at each of these beaches. The next thing we can do is we can plot the maximum allowable E. coli concentration of 235 organisms per 100 milliliters, which is represented by this green dashed line. From here, we plot our spring data. This shows all the individual data points collected between March 15th to May 23rd from 2008 through 2020. The existing load for the spring season is also plotted, which is represented by this red dotted line. The existing load is the 90th percentile for all the spring samples collected. And in this case, it shows that our spring loading is above our allowable concentration of 235. The difference between these two lines is the amount of E. coli reduction needed to bring this beach into compliance with water quality standards. From here, we can plot our spring data points. And it's pretty much the same thing. The existing load in the spring is represented by this red dotted line, which again is above our allowable concentration of 235. And then we can plot data collected in the fall. And our fall loading is represented by the black dotted line, which is below our allowable concentration. So we can, this is one way of presenting the data. We can present it in another way by putting it into a table. So again, here's Brushy Creek Lake. This top table is the E. coli represented or shown in concentration, the number of organisms per 100 milliliters. We have our observed load, remember, which was the 90th percentile of all the data points within that particular season. We have the allowable load, which was the 235 organisms per 100 milliliters. And then we have our departure, which is the difference between the observed load and the allowable load. This represents the amount of E. coli reduction needed to bring the beach into compliance. And from here, and this line is the percent reduction. That's the percentage of the observed load, the reduction required from the observed load to meet this allowable load of 235. These other values here, and we'll talk a little bit later, This bottom table is the same information, just presented differently. While this top table here is in a concentration, this table here is in a mass or total loading, which is, to come up with that, we take our concentration and multiply it by the volume of the swimming area or the nearshore beach volume. And we can see from looking at the two tables that it provides us with the same information, that during the spring and or summer, there's a reduction needed in E. coli to meet water quality standards. And in the summer, and that reduction is the same for both tables. So what is a TMDL? And this slide represents and shows an EPA definition of it, but in short, it's the maximum amount of a pollutant the water body can assimilate and still meet water quality standards. As we've shown before, there's a little bit of math involved, and before I go into more of the math, I want to talk a little bit about the potential sources of E. coli in these beachshed areas. Potential sources can be categorized or broken up into two separate categories, the point sources and the non-point sources. The point sources are those sources that require a discharge permit. One example would be a public or privately owned wastewater treatment plant. Those systems require an NPDES permit for their discharges. Those permits have a limit on what they can discharge to the receiving body of water. Now, remember that our area of focus for this water quality improvement plan is the beachshed area. And these are very small and limited areas. And in these three beaches, there are no point sources. So we don't need to consider any point sources in our calculations and determining our TMDL. The non-point sources are anything that does not require a discharge permit, and that could come from several sources. It could be septic tanks. It could be, as Jason mentioned, direct deposition in the lake itself, fecal contamination from waterfowl on the beach. Again, direct deposition of fecal matter from wildlife and domestic pets, and from the E. coli being retained in the sand environment and finding its way into the swimming area or the nearshore beach volume. Again, our non-point sources are anything that do not require a permit. So, kind of explaining our TMDL in a different way, and Jeff kind of used his pack mule with his cart, and I use it. I compare the TMDL to our household budget. We can start out with our spending habits, And we certainly always want to make sure that our spending does not exceed our income. And in those cases where it does, it would require us to evaluate our habits and make necessary adjustments. So with our household budgets, we can break it into our spending categories. Can be basically broken into three categories, which would be our fixed costs, which would include rent, insurance, a mortgage payment, things that aren't going to change from month to month. They're going to be consistent. And we have some variable costs, and these might vary from month to month or week to week, which could include groceries, clothes, entertainment, fuel. And then we have some unexpected costs, things that we want to put away for a rainy day. So could be savings, to account for major auto repairs or home repairs, something along those lines. But something that is not normally addressed in our daily or monthly budget. So through a little bit of adjustments and tweaking, our spending habits meet our income, and we balanced our budget. Now, when we compare that to a TMDL, we start out with an existing water body, and it has an existing pollutant load in it. And eventually, we're going to want to compare that existing pollutant load with what our water quality standards are, or our spending compared to our income. In the case where our pollutant exceeds our water quality standards, there needs to be some adjustments made to bring it into compliance or to meet that budget. So if we look at a TMDL still from a budget perspective, we have fixed loads or fixed sources, variable sources, and unexpected, or in this case, we're going to call it a margin of safety. So our fixed costs or our fixed loads are those point sources. Remember, we talked about point sources being those sources that require a permit. Our variable sources would be those non-point sources, things that are associated with runoff or that has variable conditions associated with it. And then we're going to have some kind of a margin of safety or savings to set aside for any unexpected, unforeseen circumstances that we may encounter later on in the future. So with that, then we do make our adjustments, and in time we're able to bring our pollutant loads down to match our water quality standards. Which would take obviously some work and cooperation between local landowners, business owners, and local agencies to meet those water quality goals and standards. We can put this into an equation. So with our budget, we have, remember, our fixed costs or fixed bills, our variable bills, and then our unexpected costs, our savings. And looking at it from a TMDL, we have our point sources, our non-point sources, and that margin of safety. Might note here that sometimes our point sources are referred to as waste load allocations, and our non-point sources are referred to as load allocations. And again, we have our margin of safety. So our TMDL is equal to the summation of all of our waste load allocations plus the summation of all of our load allocations and our margin of safety. And our target goal, our TMDL target goal, is a concentration of 235 organisms per 100 milliliters, or in a mass loading as represented here. Since we mentioned that there are no point sources in this beach shed area, our waste load allocation is 0. Our margin of safety is 10% of our target. And the difference between our target and our margin of safety is available for our load allocation or non-point sources. So putting all of this information in tables for all 3 beaches, Brushy Creek, Lake Aquabi, and Lake McBride. And this is all in concentrations. And we've talked already about Brushy Creek, where we are not meeting water quality standards in the spring and summer. We see here in Lake Aquabi and also in Lake McBride, water quality standards are not being achieved in the summer months. Again, we have our observed loads, allowable load, our departure, and our reduction. Again, presenting this information in other tables. This is the mass load for each of our lakes. Again, it shows the same thing. Reductions are the same. It just shows it in a mass load or total load as opposed to a concentration. So there's some work to be done at each of these beaches. So the next thing we want to talk about is an implementation plan. The implementation plan discusses some possible solutions to helping resolve the issues, our E. coli issues at each of these beaches. One of these strategies is raking activities or grooming strategies. This is a picture of a beach being raked, which is being executed by Iowa DNR park staff at McIntosh Woods State Park. Beach raking or grooming is the practice of removing debris and other material from the beach environment. It typically includes pulling a mechanical rake behind a tractor. The rake is on a rotating mesh belt with tines that extend into the sand, picking up debris and other material. And the mesh belt allows the sand to fall back to the beach, and the debris is deposited into a hopper where it can be disposed of. This is just one method to help clean up the beach environment and reduce E. coli in the swimming area. All right, thank you for watching this presentation today. If you have any questions or comments, please send them to either myself at james.hallmark@dnr.iowa.gov, Jason Palmer at jason.palmer@dnr.gov, or to Roger Bruner at roger.bruner@dnr.iowa.gov. We must receive these comments by Monday, October 4th, 2021, which is the end of the 30-day public comment period. Again, thank you for watching this presentation.